Okay, so today we're going to look at Rolle's theorem. Now, Rolle's theorem is basically really simple. It's very related much to mean value theorem in the fact that you can have 2 points on a graph, but the only difference is you can have the end values be the same. And what that creates is no matter how I try to draw my function, somewhere in the graph the slope is going to equal 0. The slope of my tangent line equals 0. No matter how I draw my graph, connect them. I could even draw a straight line. Now, in fact, if we do that, we get our secant line right here. I can look at my slope of my secant line, and I know that that's 0. And you can kind of see how this is going to be related to MVT, that the slope of the tangent line equals the slope of our secant line. It just so happens for Rolle's, the slope of the tangent line therefore must equal 0, and that's Rolle's theorem. So, kind of like MVT, we first have to state that the function is continuous on the closed interval a to b. Then we have to state that, too, that the function is also differentiable. So again, it's just like Rolle's on the interval, open interval a to b. And if that's true, we actually have a third step for Rolle's. The only difference, this is the difference between MVT and Rolle's. In Rolle's, we have to say that the end values are the same. F of b has to equal f of a. And if this is true, if you think about it from like MVT, where f prime of x equals f of b minus f of a over b minus a, well, if f of b equals f of a, this whole equation becomes 0 right there. And that's straight from mean value theorem right there. And if all of this is true, then we can say that Rolle's theorem applies. Or I like to rhyme it, so Rolle's holds. And somewhere on the interval, and we can use open interval or closed interval, it just depends. I think nowadays they prefer the open interval. Somewhere on the interval a to b, we can say that the slope of the function has to equal 0. And from MVT, that's our instantaneous rate of change. That's our average rate of change. And we can see that from up here. So let's take a look at an example here real quickly. If we take a look at the parabola, let's take a look at an example. If we look at the parabola, f of x equals x squared, and we'll go from the domain from -2 to 2. And I want to see if the mean value, if Rolle's theorem can apply. And it's very easy. One, x squared is continuous. F of x is continuous on the interval -2 to 2. And 2, f of x is differentiable on the open interval -2 to 2. Oops, sorry, soft bracket. And the third step says, well, is the value at -2 the same as the value at 2? I could plug that in and figure it out. 4 does equal 4, so that's true. So what we're then saying is that the MVT holds. And somewhere, we don't know where yet, on that interval, -2 to 2, the slope must equal 0. That's what Rolle's guarantees, because I'm starting and ending at the same spot. No matter how I draw, if I start in the same spot, I have to have a slope of 0. Even if I do something, even if I do crazy stuff, wiggle, 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 I have lots of places where the slope is 0. I have many places right there. So what this is now telling us then is now I have to solve it, and this is the most important part. 1, you need all of these. 2, you need to show that the MVT, that Rolle's here applies. Sorry about that, I said MVT, but I meant Rolle's, of course, so we're working on Rolle's theorem. How silly of me. So you have to show that Rolle's theorem applies, and now we have to find out where it occurs. So I take the derivative of my function. 2x equals 0, x equals 0. So it tells me it holds at the origin right there. And we can do this for multiple types of functions. Ready? We can work this with trig functions. Let's say we have y equals a sine of 2x, and we can go in the domain from 0 to, let's say, 2 pi. Okay? 1. We know sine is continuous, that the function here is continuous on that interval, 0 to 2 pi. You have to say it. Don't just think it. Yeah, I thought it was there. You have to say it. F of x is differentiable. Okay, you have to say it on that open interval. You have to say it. 3, because we're using Rolle's theorem, we have to say that the start value at 0 equals the end value at 2 pi. Sine of 0, 0. Sine of 4 pi, 0. It works. Now we have to say the next part. Rolle's theorem applies or holds on that interval. And somewhere, I like to say somewhere, on this interval, 0 to 2 pi, the slope must equal 0. It must equal 0. Once you have all that, need. Now, where does it occur? That's where does the derivative equal 0? If you notice, this is a critical number. Rolle's theorem guarantees we have critical numbers. That's amazing. We're guaranteeing ourselves that we have a critical number somewhere there. So we take the derivative. Cosine 2x times 2 equals 0. Add 2 doesn't really matter, it just goes away. Where does cosine equal 0? Well, we know that it's going to be pi over 2, 3 pi over 2. But because it's twice, got to go around again. 5 pi over 2, 7 pi over 2. And I divide everything by 2. So we get pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And we get your answer right there. Okay? So, and it has a lot of roll, and that's how we work Rolle's theorem. So if you have any questions, please come talk to me, okay? Or email me, and I can be more than happy to help you out with this theorem, okay? I'll see you guys in class. Bye.